Let us talk about iterative pre-order traversal. We are given a binary tree. We need to do traversal of this binary tree in pre-order fashion, and we need to do it without recursion. So if this is the binary tree, pre-order traversal of this binary tree is 10, 20, 40, 50, 30 and 60. In pre-order traversal, we visit the root node first. In recursive pre-order traversal, we visit the root node first, then we recursively traverse the left child or left subtree, and then we visit the right subtree recursively. Here we need to traverse the tree without recursion. We need to use iteration and some other logic to do the pre-order traversal. Let's see this example. In this example, the pre-order traversal is 10, then 20, then 30, then 40, then 50, 60, 70. We visit the root first, then its left subtree completely, then its right subtree. Visited 10 first, then 20, then this subtree. And for this subtree, we followed the same approach. Root, then left subtree, then right subtree. If we are given a tree with a single node, we need to print this node. If we are given an empty tree, we need not to print anything. Now please pause this video and try to think of an iterative solution that takes root of a binary tree as an argument. This function should not have any return type. It should simply print the pre-order traversal of binary tree using loop. Let's get an idea of pre-order traversal. So in this function that we are going to write, we are given root of this binary tree. So we'll begin from the root. And we all know that in pre-order traversal, we are going to print the root first. Root is going to be our first thing that we are going to print. Then we are going to go to its left child and we are going to print 20, then its left child 40, then its left child 80. So printing this path is straightforward. We know that this thing is going to be printed first, the leftmost line of your binary tree. How do we print rest of the nodes in the correct order? Let's try to understand the order for remaining nodes. So we started from here, then we came here, then we came here, then we came here, and we kept printing these things. So we printed 10, 20, 40, 80. Now when we are here, we need to go back to this node, right? The node that we just visited before it. Then we need to go to the right child of this node, right? And once we are done with the right child of this node, we need to go back to this node and process the right child of this node, right? Whatever is there in the right child, those all things should be processed. Then we need to go back to this node and process the right child of this node. And whatever is in the right child of this node has to be processed. So we came down and we did not have track of the previous nodes that we visited. So we need extra space or extra data structure for maintaining the previous items that we visited in pre-order traversal. And in what order we need these previous items? We need them in last in first out order. See, you visited 80 last, right? Then you are going to go to 40, right? Which is the last inserted items before 80. After 40, you are going to go 20, then you are going to go 10, right? So you are going to process the nodes in last in first out order. So we use stack data structure here. Now you have enough idea about the implementation. You know that you need to visit from the root. Then we need to use stack data structure. And we need to store the items in the stack and then fetch the items from the stack once we have processed the current node. Now please pause this video and try to implement an iterative pre-order traversal using stack. Let us now see implementation of iterative pre-order traversal. Here is C++ code and here we have Java code to do iterative pre-order traversal. What we do in this implementation, we first check if the root is null or not. We check for the corner case. If root is empty, then we simply return. We don't want to print anything in this case. Then we create a stack. As we discussed earlier, we are supposed to create a stack so that we can have the items in LIFO order so that we can process these items to print the pre-order traversal. After creating the stack, we push root into the stack first. So the idea of this implementation is similar to breadth first traversal or level order traversal of binary tree. In BFS traversal or level order traversal, we use a queue. We push root into the queue. Then we dequeue an item, we print that item, and we enqueue left and right children. Here we are using a stack, so we will push right first and then left, because you want left to be at the top and left to be processed next. So you first push right and then left, so that left remains at the top, and next time when you extract an item from the stack, it's the left child. So that's the idea. We are creating a stack, pushing root to the stack, then we are running a loop while stack is not empty, take out an item from the stack, print the content of it, and then enqueue right and left children of it if they are not null. Right? Let's see the working of this. So first we have 10 into the stack initially, then we run an iteration of this loop. Inside this iteration, we take out an item, we take out 10 and we push 30 and 20. We push the right child first, then the left child. Now we again do an iteration, and this iteration we again take out the top item, we take out 20 and we push its right and left children. So we push 50 first and then we push 40, right? And after that, we again take out an item, we take out 40. 40 does not have any child, so we do not push anything to the stack, we simply print 40 and we proceed. In the next iteration, we take out 50 from the stack, we print it, and 50 does not have any children, so we do not push anything into the stack. After this iteration, in the next iteration, we take out 30 from the stack, we print it, and 30 has a child 60, so we push 60 into the stack. And in the next iteration, we take out 60 and we print it. So this is iterative pre-order traversal. It requires big O of n extra space for stack, and it works in big O of n time.